Welcome to the 22nd lecture video for Physics 4C. We are continuing our fully quantum mechanical treatment, working out the parts of wave mechanics that are still accessible at our level, and pointing out some salient features of wave function solutions given in the textbook. We start this lecture with an introduction to expectation value and how to calculate it using normalized wave functions. We explicitly show how to calculate the expectation value of position, momentum, and momentum squared for the energy eigenstate solutions of the particle in a box setup. Then, we look at some features of the quantum harmonic oscillator. While the potential V of x for the harmonic oscillator is too difficult for us to solve the Schrödinger equation with in this class, we can still look at the solutions given in the textbook and draw connections between classical simple harmonic oscillator and the quantum harmonic oscillator, in particular in ways that illustrate the correspondence principle. And finally, we look at a demonstration of a coupled oscillator from earlier in the semester, which is a direct analog to a quantum mechanical double well potential. We will use a PHYS simulation to illustrate this analogy. For the second lecture this week, we will look at the one other potential V of x, which we will actually solve for in this class, step potential, matching the boundary conditions to derive the reflection and transmission probabilities of incident particles. Thinking about what is meant by expectation value. How many here have heard the phrase expectation value? What class have you heard of it?
In high school, statistics.
Statistics would have been one place. Anyone else have taken statistics? No? Has anyone here heard the phrase that lottery is tax on the people who can't do math? I mean, we do get lottery funding, so maybe I shouldn't say it, but it is tax on people who can't do math. So in what sense do they mean that you can't do math? I mean, you win the lottery, you win $30 million. Why don't you pay however much the ticket is? $5, $10? $1? Whatever. Why would you pay $2 for a chance to win $30 million? Because the odds are so low. And how you show that mathematically is through expectation value. So this is how you calculate expectation value. And I guess a lot of you don't have experience buying lottery. So let me give you an example that's a little bit closer to home, maybe a little too close. This is how I came up with the formula that was applied, or that I said would apply to your multiple choice, where if I were to fill out your answers, then I'm gonna take a quarter. So let me tell you what the expectation value of your multiple choice exam score is if you are guessing randomly. Let me start out with a simpler example. If you have 100% chance of being correct for 35 questions, what score do you expect to get? Yeah, 35 out of 35, right? Now, what if, so if you're guessing randomly and every question has 4 choices, for example, then what's the chance of you getting a question correct by simply guessing randomly? 1 out of 4, or 25% chance of being correct. So I think if I asked you the question, most of you would answer then, not rounding anything, you would be, I don't know, is it 8.75 out of 35? That would be, like on average, this is what you would get. by simply guessing randomly, right? And here's how you would kind of expand out this calculation. So I hope these make intuitive sense, just from your basic number sense. How you would expand it out is this. So you have n event. So 35 questions, those are n event. So sum of I going from 1 to 35. And let's say Pi, that represents your chance of getting a question correct. So in this case, each one of those is 1/4. You multiply that with the number of points you get. In our case, that would be 1. Right? So that would give you, oh, well, actually, you know what? That would give you 8.5. Well, I'm not quite doing this right. So, and yeah, I'm being a little bit more murkier than it should be. So that's 8.5. I guess the way I'm applying the formula is a little bit different. I probably should have used the example of SAT, but I don't think SAT does this anymore. SAT exam used to take points off for the questions you attempt to answer, and then you get wrong. Do people remember that? Yeah, they used to do that. For a multiple choice question of 4 choices, for every wrong answer, they would take 1/3 of the points off. And their reasoning was this kind of expectation value calculation. So imagine someone who's guessing randomly. For every question they answer, they have a chance of getting the question right and getting 1 point there. And so this is the case where it's correct, which means the expectation value of someone guessing things randomly would be whatever number of questions divided by the chance. So what they've done is they adjust that expectation value by, so you can think of it as this math question. So this is the end result when you get something correct. When you get something incorrect, then you have the, let's say Q of I stands for the probability that you are incorrect on that question. And this is the exercise. What should the point that you assign in that case be so that this adds up to 0? So that someone who's guessing randomly ends up with a score of 0. What's the probability that someone's incorrect? So, yeah, we said this is 1/4. So the probability that someone's incorrect is 3/4. So what should the value of x be so that this adds up to 0? Minus 1/3, right? So if this x is minus 1/3, then you know you get plus 1/2 minus 1/4 as the expectation value of the chance of the event when you are incorrect. So what we call expectation value is the average of all these possible outcomes. So let me describe what happens with the lottery, and then we'll go into break. And when we come back from break, we'll talk about how this applies to quantum mechanics when we are actually trying to do, not trying to make money on lottery. So do some people here know the lottery prices? No? I'll just make up some number. Let's say a lottery ticket costs $5 as an example. And usually many lotteries are set in a way your probability of winning is at some fixed percentage because you are guessing some number in a sequence of numbers. So let's say you have 1 in 10 million chance of being right. Now, here's a maybe surprising fact. So some lotteries are run in a way that if there's no winner, the pot keeps accumulating, right? So then next week, there's a bigger pot. At some point, the pot can be so big that your expectation value from buying a lottery ticket can be positive. So the question here would be, well, how big would that pot have to be so that I expect to get something greater than 0 from buying this lottery ticket? Well, let's just do the calculation. So we won't bother with the sum. We are just dealing with 2 chances. So chance of winning the lottery, let me write down that as one term, plus chance of losing the lottery, which is what a lot of people are doing. So when you lose the lottery, what's your outcome, money-wise? You lost $5. So the outcome here is minus $5. What's the chance of that happening? 1 minus some 1 in a, so I guess that's practically 1, right? Practically 1, so I'll just say approximately equal to 1. So what's your chance of winning the lottery? Well, it's 1 in a 10 million. So your chance of winning the lottery is 1 over 10 to the 7, 1 in 10 million. So now this is the question. What should the jackpot be so that when you add this up, you get something that's bigger than 0? 50 million, right? Yeah. So if the jackpot is as big as 50 million, then your expected winning or expected result from lottery can be, so it's no longer taxed on the math illiterate. It's now whoever is there to win. Now, so that's what we mean by expectation value. And I want to separate this. The whole concept of expectation value, when I first learned it in quantum mechanics, it was revolutionary because that helps you strategize. It helps you think in a way that a lot of people don't learn to do unless they've taken statistics. But you want to sort of separate out this whole expectation value that represents what you would get if you play the lottery 10 million times or something. If you don't play 10 million times, then your result is kind of one or the other. So the expectation value being positive doesn't mean that it's actually concretely positive to you. But so this is an extreme example. With the quantum mechanics, we can talk about more, less extreme on either end. We will show some examples of calculation using these wave functions and the interpretation of the how you get probability density from the wave function. So let me ask you about one more idea that relates to what we are going to talk about. So we talked about expectation value, which might have been a bit new to people. How about weighted average? Do you remember that? Let me give you an example of weighted average. Once again, your grade. So this is how your grade is actually calculated. And if you want to kind of project how well you'll do overall, this is how you can do it. So according to your syllabus, this is how your grade is set up. The lab is worth 20% of grade. Homework is worth another 20% of grade. Multiple choice portion of midterms are worth. Okay, this is not a good example. Let me give you the example for my other class, Physics 10. They have more interesting breakdowns. So for Physics 10, one kind of homework assignment has a grade of 20% overall. They have a second kind of homework assignment, which has grade of 10%, and they have peer grading, which is the same thing you guys do, that's worth 10% on its own. And they have midterm exams, which is worth 30% on its own, or all the midterms together. And the final exam on its own is worth 30% of their grade. So their weights are more interesting. So how do you do weighted average? Anybody here know the formula? Okay, I'll be multiplying with these at some point. Let me give them a symbol. W1, W2, W3, W4, W5, or Wi. Okay, so what am I multiplying this Wi's to? What am I multiplying it to?
The score.
The score in the category, let's say from 0 to 100%. So score in each of the categories, I. Okay, and then, so I have 5 of these multiplied numbers. What do I do after? Yeah, you add them together. You add them. And then anything else after that?
Divided by 5.
Not divided by 5. That actually gives you a wrong answer. So
Divided by the sum of the weights.
Yeah. So in the generalized case, when you're doing weighted average, that's what you're supposed to do. So multiply each of the thing you want to average by the weight, and then add them all up, and then divide the whole result by the sum of the weights. This is the average score, or weighted average score. Yep. Now, this is a special case where if you add up all the weights, you'll get 100%, so that this division won't do anything. Now, when you actually look at your gradebook right now, your gradebook currently is, or their gradebook, which is similar to your gradebook, is currently actually operating without a final exam score, which means the sum of all the weights do not add up to 100%. In your case, they actually add up to 80%. So in the background, this is what Canvas is doing to give you your overall percentage, which tells you that your homework is being overcounted and your exam scores are being undercounted right now. If you know how weighted average works. But this is weighted average, and this is something you might have seen other people do. Now, what I will tell you is this. Expectation value is a type of weighted average, where the weights are, so in a weighted average, weight can be really anything. In fact, the way I teach physics 4A, the center of mass is the weighted average of position, where the weight is the mass of the thing. So if I want to get expectation value out of it, expectation value, then what I do is where I have weight here, instead of weight, it becomes the probability of that particular outcome happening. You multiply that, add them all up, and then you divide it by sum of all probability of all the outcomes happening. Now, if you normalize it correctly, then the sum out to be 1, and this shouldn't do anything. If you didn't normalize correctly, then this step actually does the normalization for you at the very end. So let me do a couple calculations with the actual wave function to show you how this works. So this is now actual quantum mechanical calculation. These expectation values are what you use to represent likely outcome of an experiment. So we are measuring, when you are talking about expectation value, you are calculating some physical quantity. So remember back at this picture, we are imagining a particle, let's say an electron, that's trapped inside a box. What kind of physical properties can you measure for this electron?
Position and momentum.
Okay, we can measure the position and momentum. Anything else? I guess that's actually kind of it. Anything else you can build up from position and momentum? Like if you're on energy would be p squared over 2m. Right? Good. All right, so let's try to measure the expectation value of the position for this electron, which will be fun. Now it's fun, and you actually know the result before you do any calculation, which is kind of good for introductory calculation. So when so for this electron, when I calculate the average x value, or I'm going to use this symbol to denote it, x inside the angle bracket. When I calculate this, what do you expect it to be? Pardon the pun. You expect it to be in the middle just based on how this wave function looks, right? What about for E equals 2 state? Now that's where they are most likely to be found, but what about the average position? Still middle, right? Same thing for here, E3? Same thing for all of them, right? So let's try doing it for general state here with just n, and see if we get the expectation value of the particle being in the middle. So I'm saying that this is equal to expectation value of x, or the way I was describing this expectation value before, I need to find probability of the electron being at a particular x location. This is probability of a particular event happening. And if the electron was at this x location, then the outcome would be, well, outcome would be x. Right? Yes? Okay. And the way I was writing it before, I would sum it all up. I going from 1 to some value divided by sum of all the probability of particle being found at some location x. But since we are dealing with a normalized wave function, let's trust our normalization and say that this will be 1 when we do that calculation. So we won't redo that calculation. This is a little bit problematic because this is a summation symbol. But what we have is a smooth situation. So really, conceptually, the way this works is, let's say you have, so the probability density for this ends up being something like this, right? Psi absolute value squared, right? And when we say P probability being found at some location x, what we really mean is not being exactly at that location x, but x plus dx. So this is x plus dx. And the probability of being found within this location here, that probability is probability density at position x times the interval dx. Good? So what I wrote as P sub x is really probability density x, and then I'm just going to multiply dx here times the dx. So these two multiplied together is the P sub x. And how many of these intervals do we have? Infinite number of them, right? For infinitesimally small dx. So what does this sum become? Integral, right? Yeah, it goes from the Riemann sum to the integral. That's the limit. So in the limit where dx goes to 0, it's infinitesimally small. The summation becomes integral from x equals 0 to L. So that's the formula. It's quite simple. It's actually, let me write down one more step to actually give you the quantum mechanical formula. So this probability density is psi squared. So this expectation value of x is integral from x equals 0 to L, psi of x squared times x dx. Doesn't seem all that hard. So let's try writing it out and see if we can do it for an arbitrary energy eigenfunction. And see what we get. So we are integrating from x equals 0 to L. Let me write this out. Guess we have this. So after doing square, we get 2 over L times sine square of n pi x over L times x dx. Anybody here know how to do this integral? Yeah, I'm not sure. Yeah, I don't really want to do integration by parts. Let me use Mathematica. So this is the integral. And if you really wanted to do the integral, you can do integration by parts. You know, this is your u, so it'll eventually be differentiated into nothing. And this is, yeah, so I don't want to do that. So let me use Wolfram alpha. I think this is easy enough for Wolfram alpha to do it. So what I want to do is I want to integrate sine squared n times pi times x over L times x with respect to x from 0 to L. All right. Alternatively, you do, oops, that's not right. Let me do it this way. Sine of, it misinterpreted me. Alternatively, you do look this up in an integration table. And wait, that doesn't seem right either. Indefinite, definite integral from. I think I might have done something wrong.
You didn't put the 2 pi over L.
Hmm?
You didn't put the 2 pi over L.
Oh, 2 over L, that's just, that's constant. So I don't need it, I just wanted this part done. I guess what I was hoping was, but these would simplify to, sorry, Mathematica is very, or anything Wolfram is very paranoid about doing simplification. It's assuming n is a really general number. So what it really meant to say is this is equal to 0. Because, 2 pi n is, for any integer value n, it's 0. And what it really meant to say is this is equal to 1. Because 2 pi n for any integer n is 1. Good? So 1 minus 1, well, that's also 0. So it does simplify down to what I want. Minus, so plus 2 pi squared n squared L squared over 8 pi squared n squared. So let me do this cancellation here. Pi squareds cancel, n squareds cancel. I guess, so I have 1/4 L squared. So that's the result of this integral here. This integral here will give you L squared over 4. Now you multiply 2 over L, and you end up with the expectation value of L over 2, which is what we are expecting. Good? Kind of gives you confidence that this is how it's supposed to be. Gives you confidence that this is how it's supposed to be. Now let me ask you a more difficult question. So I guess we want to calculate the momentum, average momentum of these states. Right? That's a reasonable question to ask, right? So if I calculate average momentum of these states, as in if I calculate the expectation value of momentum, What should I get? Do you have some sense of what correct answer for that?
0.
Gauge says 0. How many people agree? Not sure? So, well, if your intuition says that it shouldn't be 0, why would you say you don't expect the momentum to be 0? Anyone else here expect the average momentum to be 0 other than Gauge? Ben, can you explain why average momentum should be 0? Yeah, the standing wave is a combination of one wave traveling to the right, another wave traveling to the left. So there is, so the magnitude of momentum won't be 0, but the momentum with the signs, plus, minus, add up, they are 0. So we should get 0 momentum as our answer. Now this is where I need to introduce a little bit more of the formalism than we have so far. So this was all fine to write, right? With the momentum, if I try to write down the same thing, it doesn't quite work. As in, if I try to write down, all right, expectation value of momentum is equal to x equals 0 to L, probability density times momentum times dx. Then P, I'm treating it like a variable, but when you look at this wave function, there's not a single P. So here is where you have to be careful in how you measure momentum. How did we talk about measuring momentum before exam 2? We talked about some mathematical procedure we can use to get the values of momentum.
Operator.
We use operators. We introduced this momentum operator. Momentum operator of, I think, a minus I h bar partial derivative with respect to x. Is that coming back? Yes, no? All right. So when we want to measure momentum, this is what we would do. We would say apply momentum operator to some momentum eigenvalue, momentum eigen function, I guess in the position representation. Then if it's a momentum eigenfunction, then you should get the same function back. And then you would have momentum as a number in front of the function. And this is what we saw with the traveling wave solution, right? Is that ringing a bell? Yes? When we were dealing with this, so this is an actual momentum eigenfunction. Let me write it down as a time-dependent wave function. This traveling wave, plane wave solution, some amplitude times e to the I, kx minus omega t. This was a momentum eigenfunction. It has momentum traveling in one direction, momentum value of h bar k, and all of that came out when you apply the momentum operator. That rings a bell? Yes? Now, these are not momentum eigenfunction. And you can kind of see that here because when you apply the momentum operator, you don't get the same function back. And the reason for that is, well, it doesn't have one definite value of momentum. It has at least 2 values of momentum, possibly more. So if we wanted to use this process to simply try to measure momentum, you can, because there's not one single value to measure. But what you can do is you can calculate the average momentum. And that's where this process of expectation value comes in. And I was kind of a bit sloppy in writing this version. Let me be a little bit more careful in writing down the actual correct formula for expectation value for any general operator. So this is how it should have been written. It should have been written this way. So you have the measurement of the value. So it would be the operator acting on the wave function. So this is the this is the mathematical procedure that takes a measurement of the value. And in the case where this is a combination of different momentum eigenvalue states, as in this state is combination of different momentum states, then this won't give you a clean result like this. So to get the expectation value, what you do is take this, multiply it by the complex conjugate of the wave function, and then take the integral with respect to this coordinate variable x over all space. Or in our case, what all space is ends up being just from x equals 0 to L. Good? And you can kind of see that if we use this operation, back here, this was all just fine. Because x, it's just multiplication by a scalar. It just moves through different places. This is where you have to be careful. Because when you are acting with the derivative operator, the order matters. So that's why I have to be more careful here. Okay, let me go through the calculation and see if we get what we were intuitively expecting to get, that our momentum should be 0. Okay? So, all right, let me write it out. So it goes from, integral goes from x equals 0 to L. This, well, these are all real valued functions, so the complex conjugate doesn't do anything. So square root of 2 over L, sine of n pi x over L. I'll just keep it as general n again. Whatever the n value is, it should still be 0. Times the momentum operator minus I h bar, derivative with respect to x, and then the function square root of 2 over L, sine of n pi x over L dx. Okay. All right, let me pull out all the constant coefficients in front so that they are not bothering me. I have square root of 2L, 2 of those, so 2 over L. I have minus I h bar. Let me rewrite it this way. H bar over I, because it's, I don't know, looks simpler to me. And I think I can write down the rest. So it's still under the integral. I have this function still, sine of n pi x over L times, okay, I have to do this derivative. So use the chain rule. The factor inside comes out. So I have, I guess, let me keep track of the factor here. So factor that comes out when I take one derivative, that's going to be n pi over L, right? And the derivative of this is outside. So derivative cosine, sine gives me cosine of n pi x over L. And the derivative of the inside gives me the factor n pi over L, which I put out here. And I guess I'm done, dx. Before I go any further, anybody here know by sight what this integral should be? If you have enough experience with the trig identities, you might recognize it now. If not, I can spell it out. Not yet?
Double angle formula.
Yeah, you use double angle formula that'll quickly tell you what it is. So this is the formula I'm using. Sine of 2 theta is equal to 2 sine of theta cosine of theta. Because that's what I'm seeing here. Sine of angle times cosine of angle. So what I can rewrite this as is sine of 2 n pi x over L, I guess, divide by 1/2 or multiply by 1/2. What is integral of this from x equals 0 to L? 0. It's an integration of a sine function from x equals 0 to L plug in L. It's 2 pi n, or the integer multiple of a cycle. So yeah, so this entire integral, when you look through those expressions, ends up being 0. Meaning all these factors don't matter, it's 0. So yeah, you get expectation value of the momentum to be 0, which is what you're hoping to get. Okay, let me wrap this up with one, I guess, slightly less trivial calculation. Everyone okay with this calculation? Yes. Okay, one slightly less trivial. Okay, so expectation value of momentum is 0. What about p squared? Not momentum, but momentum squared. Is that still going to be 0? No, like intuitively here, it shouldn't be 0, because intuitively, this is what you know of the, I don't know, momentum distribution. The distribution of the different states as a kind of function of momentum eigenstate. What you have in this setup is you have one value at where momentum value of, I don't know, momentum value 2h over nh over 2l, and plus nh over 2l, and another value at another state at the value of minus nh over 2l, right? So that's why when you took the average of these two values, you got 0. But when you are dealing with momentum squared, then it changes. Because this thing squared is not minus this squared, it's just plus this thing squared. So if you look at the distribution of momentum squared, it would look like just at a single value, n squared h squared over 4l squared, you will have all the states and nothing else anywhere else. So you should get back to essentially what relates to the absolute value of momentum, not momentum with a sign. So let's see if that's what we get. We are going to do expectation value of momentum squared. Yep. So when you do that, then let me just make the changes as I go. So before I was measuring momentum, just one factor of momentum. If I'm measuring two factors of momentum, then I kind of just apply this twice to that thing squared. So if I'm doing that, I'm applying this momentum operator twice. So for this coefficient, it looks like they're just multiplying together. Minus I squared is just minus 1. And I have h bar squared. And now I have the second position derivative. Good. All right. Let me imagine pulling out the same factors as I did before. I still have the same factor 2 over L. Okay, now I don't have, instead of h bar over I, now what I have is, let me do this in purple the way I've been doing. What I have now is minus h bar squared. Yeah. When I take this derivative twice, I'm going to pull out this factor of n pi over L twice. So there's this squared there, n pi over L twice. And I guess I should now do the rest of the calculation, write down what the rest of the expressions look like. So I have, let me write down the ones I haven't handled. I have this sine of n pi x over L. And as I take the derivative, the first derivative gives me cosine of x. And then the second derivative of that gives me minus sine of x. So what I have here is minus sine of n pi x over L. And I already took care of these factors that come out. Integral for, with respect to dx, and that's it. So let me do some quick simplifications. So this minus sign cancels out this minus sign. So my overall answer is going to turn out to be positive, which is good. These two are the exact same factors. So let me just get rid of one and say this is the whole thing squared. Didn't we do that integral before? Yeah. Yeah. So you remember doing that integral before, and we ended up with, was it 1/2? No, it was, the integral was L over 2. Right? Yeah, that's the integral we did. All right, so I guess we are all done. We just have to work out all the factors to see what cancels. So this 2 cancels this 2. This L cancels this L. Then I guess that's it. So collecting all the other factors that remain, we have n pi, let me write it this way. N squared pi squared h bar squared over L. Is that correct answer? If you're not sure on this, there's one more thing you can do. You can rewrite h bar as h over 2 pi squared.
L squared, right?
Yeah, L squared, sorry. L squared. So if you write it out that way, then what you have is pi squared cancels out pi squared. So you have, so this is the simplified version. This is equal to n squared h squared over, I guess I can write this 4 L squared. And now if I want, I can put it into this form. Let's see. Square of h over 2L over n. 2L over n. I'm not doing much since we got to this expression. I'm just rewriting into a form to try to remind you of de Broglie relationship. Right? Momentum is Planck's constant divided by wavelength. So that squared is the expectation value of momentum squared. Okay. So we did these simple calculations with these very simple states. And what I will tell you is that this is a big chunk of quantum mechanics. When you do the semester-long upper division quantum mechanics, calculating expectation value is a big chunk of that. And we'll use it a little bit in this class, but not too much. Anything beyond this does get fairly complicated. So like there's a limited amount we can do in either homework or exam. But I just wanted to show you that there exists this mathematical procedure which will give you a result that represents what you should be measuring. And we already talked about that kind of with this operator, but they were applicable in a very special circumstances. Calculating expectation value, it works in all circumstances. Wherever there's physical observable, you can take an expectation value and get something reasonable. So this is the time-independent Schrödinger equation. Hopefully it's beginning to look familiar by now. Yes? No? So this one represents kinetic energy of the wave function, or the particle represented by wave function. This one represents the potential energy. And in the time-independent Schrödinger equation, this is the total energy. And you can kind of see it. This is just your total energy. And that's, so this is kind of an indicator that this time-independent Schrodinger equation, it only applies to energy eigenstates. Because where you apply the energy operator, you got a definite value for energy. So we just went over this. So this sounds familiar, right? It's not overly confusing. Okay, good. So we have actually been working with the time-independent Schrodinger equation so far. But so far, so this is the thing that distinguishes different cases. The kinetic energy term, it's the same no matter what you're dealing with. And as long as you're dealing with the energy eigenstate, this term is also the same no matter what you're dealing with. The only term that changes, and that's what makes this so interesting, is the potential energy term. So the reason I have said multiple times that this is the simplest possible case is that for the infinite square well, the potential energy is 0 wherever the particle is. So you can just say, all right, this is 0. Let's deal with the kinetic energy equal to total energy. That's the simplest possible case. Anything else we deal with now will have non-zero potential energy, or it'll have non-zero potential. And there's 3 examples that we will really look at in this class. The first one you are seeing is the harmonic oscillator potential. I will talk over some features of it, and then we'll kind of leave it there. It's mathematically too complicated to do more. One where you might do more detailed calculation is actually with the step potential. That's where this potential function, it's a piecewise function of constant value. Because then you can solve this in different regions and then match boundary conditions, and there are things you can do. So that we might do in more detail. And the third one you will see it next week. It's the 1 over r potential, or more precisely minus 1 over r potential that you have with the hydrogen atom. That's how precise solution of a hydrogen atom is done. There also, we will just talk about the features of the solution. We won't actually do anything in the sense of deriving it. We'll just point out how that connects to things you may have learned in chemistry. So for today, quantum harmonic oscillator. We should start out with a description of the classical harmonic oscillator. So I guess this is the good place to put it. So classical harmonic oscillator is characterized by having this potential function, where the potential energy as a function of, so imagine a classical particle that's rolling around in this potential. Then you guys remember spring potential energy, right? This is the spring potential energy. So at x equals 0, you have minimum spring potential energy, 0. As you go farther and farther away, spring potential energy increases as x squared. So this time-independent Schrodinger equation for simple harmonic oscillator would become something like this. Minus h bar squared over 2m, double position derivative, plus 1/2 kx squared, wave function again, equal to E psi x. Good. And then the rest of the thing is solve this. That's the rest of the exercise. And I will tell you that this is fairly difficult. I think I told you guys before exam 2 that a physicist's most common guess is an exponential. See if an exponential fits. And here, exponential won't be a solution. In fact, even if you try complex exponential, it won't work. Is it even exponential times? There is an exponential in there somewhere, but it's not a simple complex exponential. I will show you the solutions. So what it is if we actually want to solve it, that's upper division level quantum mechanics, we are not going to do it. Let me just show you some of the aspects of it that you should be familiar with. One thing that we do is almost all the classic treatments of this do not leave the equation in this form. Let me ask you this way. If you have so this is a classical harmonic oscillator, right? You have a spring potential, and this is the thing oscillating under spring potential. What can you use to characterize this? So right now here, you've seen it characterized using spring constant K. What other parameter can you use to characterize this that would somehow relate to K, but is not K?
Angular frequency?
Something about angular frequency or natural frequency of oscillation. Like that was the one characteristic feature of simple harmonic oscillator, in that no matter what the amplitude was, small or large, the frequency of oscillation is constant. Do you guys remember that from physics 4a? Yes, that fact. How many of you remember the formula? This is a good formula to memorize. Let me write it down. I don't know. It's omega is equal to square root of k over m. Doesn't it just roll off your tongue? No? Well, it should have. But this is a characteristic of simple harmonic oscillator. This is the natural oscillation frequency. You can actually use the frequency to characterize this simple harmonic oscillator. So what most standard treatment of this do is, instead of characterizing the potential with k, it uses this relationship to rewrite k as m times omega naught squared. And it would use this frequency of oscillation to characterize the harmonic potential. So let me rewrite this way. 1/2 m omega naught squared. And this is going to come in useful in describing some things. So, all right. So I guess now this is my potential energy. And I guess that's it. As far as the classical oscillator goes, if I have a ball here, release it, and it oscillates back and forth, and whoopty. Sorry. Let me point out some features of classical oscillator that we are going to see is different with the quantum mechanical oscillator. What's the minimum energy classical oscillator can have? Not a trick question. Constant at what value? At 0, right? So if you say took a ball here and released it there, it would remain there, and you would have 0 energy harmonic oscillator, which is not really oscillating at all, but 0 energy. Quantum mechanically, what's wrong with that picture? Like if you wanted to say the same thing just in quantum mechanics, you have a wave function which has 0 energy at the bottom here, then what's wrong with that? What are some things you know about wave functions that have to be true? This is one of the fundamental relationships for wave function. It's not something we spent a lot of time on, Ben?
You can't know the position and the momentum.
The uncertainty principle, right? So you can, so let me write it down, that the uncertainty in position and uncertainty in momentum are related this way. There is a minimum value in the combination of these uncertainties. So if this says 0 energy, so that must mean 0 kinetic energy. What's its value of momentum? 0. So that has to mean it's spread out over a large space. But if it's spread out over here, then now it has some potential energy. And we want it to have 0 potential energy, which means it would have to be here. So this is something that's contradictory with just the basic nature of quantum mechanical wave function. So what you will see is that the minimum possible energy in this simple harmonic oscillator, kind of like a minimum possible energy here, that minimum possible energy is not 0. It's something else. So that's one feature that distinguishes classical oscillator from quantum mechanical oscillator. Classical oscillator can have zero energy. Quantum mechanical oscillators cannot have zero energy. The second thing is a little bit going to be even less intuitive. Let me try to describe it this way. If I took a ball here and released it there from rest, what you expect to happen is you will expect it to roll down, roll it up here, and how high up would it go? Same height where it started out from, right? So, all right, it'll come to the same height here, come to rest here, come to rest at this location, roll back down, and then it'll oscillate back and forth here, right? Let's say, you turn away for a while, and you turn back to look at where the particle is. So you will observe the particle at different locations, right? Would you expect to ever find the particle in this region or in this region? No, right? So these regions are, they come with a fancy name. The fancy name is, we call this classically forbidden region. Meaning in this region, the particle will never be found there because it didn't start out with enough energy, so it doesn't have enough energy to ever be here. I will just tell you the result. Quantum mechanically, the particle has probability of being found here. Not large, but it has non-zero, actually fairly substantial probability of being found in classically forbidden region. Like the farther away you go, the less likely it'll be, but it has a decent chance of being found, for example, in this region. It ties into the wave nature, and I think that's a little bit easier to discuss when we are talking about the step potential, so I will leave that there for now. But having pointed out those classical features, let me show you the quantum mechanical solutions. Solutions for this differential equation. Once again, we are not going to do anything to actually get these solutions, get the solutions, that's in your book, but you should know at least what they look like. So they look like this. They involve something called Harmonic polynomial and some, I don't know. I think the lowest energy state looks like a Gaussian, but I think there's some sinusoidal thing in there. So quantum mechanical harmonic oscillator, so potential, write it in this form. All right, so this is the Schrödinger equation. And so we will talk about this. So these are, when you go through all the solutions, upper division stuff, this is what you find are the allowed energies for your oscillator. And n can take values starting from 0. So your minimum possible energy is, minimum is h bar omega over 2. So that's the minimum possible energy for this quantum mechanical oscillator. Sometimes that's called the 0-point energy. And like when science fiction talks about 0-point energy, well, that's what they are referring to, or that's what their technical advisors are referring to on those TV shows or movies. Now, so this energy, these energies, so you can plug this back into here, and we'll actually do that shortly, and then find what functions satisfy the resulting differential equation. And you find that for different values of n here, you get different forms of solution that looks like this. So this is the Gaussian thing. This is the Harmonic polynomial. I thought there was also sinusoidal things here somewhere. I don't know. All right, so not important. You will never have to memorize this, but you should have a sense of what they look like. So this is the lowest energy state, n equals 0. This is the next high energy state, n equals 1. This is the next high energy state, n equals 2. And these are actually drawn to scale. This is 1/2, one whole unit over h bar omega, next to whole unit over h bar omega. It's following those energy levels that were given up here. Starting with a 1/2 h bar omega, it goes increases by an integer each time. So let me point out the feature that I was talking about earlier. So this would be the point beyond here would be the classically forbidden region. This is how much energy h bar omega, how much total energy the particle has. So classically, it could be a particle bouncing back and forth, but it'll never go beyond here. But when you look at the wave function that represents the particle, this is what you are seeing. You have this portion of the wave that is beyond the classically forbidden region. And this actually exaggerates a little bit the likelihood of particle being found here, because the probability is actually this wave thing squared. So proportionally, this ends up being smaller portion of the squared thing. But it's still significant. And the same thing holds for this higher energy. So this is the classically forbidden region. You have some wave function here. And I guess I think we'll have time to talk about this more as we do step potential. But if you have some intuition for differential equations, this is how you can kind of think about it. What do you notice? Do you notice anything about these wave function solutions by chance? What do you see in this classically allowed region as you go to higher and higher energy?
There's more node.
More node. You see it oscillating, right? So in this region, where the total energy is greater than the potential energy, that is what you are seeing. You are seeing these oscillations. So when you get solution to this equation, there are some regions where the solution you get will tend to be an oscillatory solution. And there are regions where the solution you get will tend to be an exponential decay solution. Let me rewrite that a little bit. Let me rewrite this Schrodinger equation to give you that sense of intuition. So I'm going to rewrite it this way. I'm going to solve it for this highest order derivative. So when I do that, this is what I end up with. Highest order derivative is equal to, so I moved this over, so E minus V. So E minus V of x. And then I divide up by this. So it's minus 2m over h bar squared, and then psi x. Okay? This is how you get some sense of intuition with this. So you're not trying to solve this because this is a functional position. It can get complicated. You're just trying to see intuitively how does the solution behave. And the key here is that you have the second derivative, which will give you your function times some kind of a number. And this number can be divided into, well, at least two distinct categories. If E is greater than v of x, then this number is negative. Right? And if E is smaller than v of x, then this number as a whole is positive. Okay? Imagine you have a simpler differential equation that looks like y double derivative is equal to minus ky, which would kind of correspond to this. What kind of solution do you expect for y of x here? Sines and cosines, right? Or complex exponentials. Right? So that's what you get. In this case, you get an oscillatory solution. You can kind of think of it as the wave, it always bends towards the zero. So when it's above here, it bends down towards the zero. And when it goes past the zero, it bends back up towards zero. So that kind of behavior leads to oscillation up and down. And what about if you have a positive coefficient here? What kind of solution do you expect for y? Exponential solution? Yeah? Can it be complex exponential? It has to be real exponential, right? So that when you take double derivative, the coefficient is positive. So it's a real exponential solution. It can be exponential rise or decay. When you match boundary conditions, you essentially eliminate whatever leads to your wave function going out, blowing up to infinity. So, and that's what you are seeing here. In the region where the energy is smaller than potential, then you get an exponential decay. You can look at it as the curvature of, which is related to second derivative, curvature of the function curving away from the zero until it asymptotically reaches zero. So that's some intuitive sense you can develop about the time-independent Schrodinger equation so that you have some sense of how the wave functions is behaving. And this is the key point that leads to there being a non-zero chance of the particle being found in classically forbidden region. Oops. The reason for this is that when this happens, when potential energy becomes greater than energy, your wave function does not suddenly drop down to zero. So it switches from being oscillatory function to an exponential decay. But depending on the decay constant, it takes some distance to decay. And in the distance of decay is where you are having a non-zero probability of finding a particle where its potential energy is greater than its total energy. Good? That makes sense? Kinda? All right, I guess that's all I have time to talk about for harmonic oscillator. The rest I'll try to put in some homework questions where you're doing some simple calculation, but once again to emphasize, you will never have to memorize any of this. Oh, I forgot to show one thing. I don't know if I have time to show it. Guess not. You can do some things with some fun things with Mathematica. So this is what I have. What I have written here is the differential equation, right? Minus h bar squared over 2m, double position derivative psi x, 1/2 mass omega squared x squared psi x is equal to energy psi x. Good? And I'm plugging that into equation 1. And my eventual goal is to plot it out. So let me just set all these constants to 1. I'm essentially choosing a unit system where h bar is equal to 1, mass of my particle is equal to 1, and the natural oscillation frequency is equal to 1. It's what they call natural unit. So let me do that. So with that unit system, this equation becomes this form. It has only one undetermined parameter, energy. So you kind of have to plug in the values of energy. Let me show you that mathematically, that energy of zero is not a possible result with this. Let me try to plug in zero energy. I want zero energy for my solution. Mathematica somehow still comes up with a solution. Maybe you have no idea what parabolic cylinder D is. I have no idea either. Mathematica has a lot of special functions. Most of them are solutions to differential equations. So what I would do instead is I would plot it out. That's what I'm doing here. That's what all these commands are doing. I'm just plugging in some parameters, either 1 or 0 for these first and second integration constants. So I do it two different ways, where I plug in 1, 0, and then 0, 1. So normal originally was an absolute value. So when you plot them, this is what you get. This is the first result. Second one doesn't give me anything. That's probably because whatever this was, this is giving me a complex value. So if you wanted to plot something, anything at all, then you can force it to say, all right, give me absolute value. Oops. Give me absolute value. Then this is what I get. Something that blows up to infinity as you go far away, or something that blows up to infinity whichever direction you go far away in. And this is what tells you, all right, so so neither of these two independent solutions can give me a real physical solution where a particle is confined within that harmonic well. This is what tells me energy equal to 0 is not possible. All right, so let me plug in energy equals h bar over 2. So that would be 1/2 in our unit system. Then this is the solution I get. I still have two independent solutions. Let me plot them both out. Then this is the solution that you saw plotted in the textbook. This is the ground state solution, and whatever this is, okay, we are gonna throw this one away because it's giving me something unphysical. Okay, let me try. Okay, so I agree that energy equal to 0 is not possible. What if I'm a little bit insistent that h bar omega should also be a possible energy? Like, why not? Well, this is why not. You get some answer, and when you plot them out, none of them are physically possible solutions because they all blow up at infinity. It's not representing a particle that's confined in that harmonic potential. All right, so you then give up and go with the actually values that are given as allowed values in your textbook. Then, so not all solutions will be physically realistic. Like this one is physically unrealistic, but this one is. This is the one solution, the first excited state solution with one node. And let me do the next to two more energy levels. So right, so 4 is not gonna work. It has to be 5. Then hopefully I have a solution with the 2 nodes. And if I do it, all right, one more, 7. 6 is not gonna work, and I do 7. Then the one of the 2 solutions I get, I have 1, 2, 3 nodes. Yeah. So that's it. You can kind of, if you want to try it out, you can do it on your own. It's fairly simple code. Oh, there's one more thing I really need to mention. This is what your book claims is an example of correspondence principle. Do you guys remember what correspondence principle is? Someone other than Gauge. What does correspondence principle say? This is a principle that's important in modern physics, both the special relativity and quantum mechanics. No one here remembers correspondence principle? I briefly mentioned it when we were talking about special relativity. It comes down to this. Newtonian mechanics, is it wrong? Is it, okay, is it wrong like alchemy was? Is it wrong like astrology is? It is still right in some sense, right? It is experimentally tested. It is a good approximation. So, all right, so we found better theories, special relativity and quantum mechanics. That doesn't mean classical mechanics you learned, it doesn't mean you have to throw them out. It just means you now recognize those are approximations. So this is what correspondence principle says. Special relativity and quantum mechanics, these are more exact theories of nature. But when you take them to the limit where the approximations should be correct, that these more precise theories, special relativity and quantum mechanics, agrees with the approximations of classical mechanics. So in the special relativity, when you took the energy for kinetic energy and took the low speed limit, we recovered 1/2 mv squared. So in quantum mechanics, the results are a little bit not always easy to interpret. That's why I'm putting on this screen, and I mean to ask you. So I hope it's clear what it's plotting here. It's plotting absolute value squared of the wave function. So the probability density of the wave function over the space of, wait, it's not showing me the, wait, I thought it was showing me, well, it's not quite. All right, let me do my own version. I don't like the version that's in the textbook. So 12, it should be 25. What? Oh, I know why. Because I'm not going from small and large enough value. All right, maybe a little bit. Let's actually go farther than what your book does. 45. So that should be n equals 22 state. Okay, I think I'm going to stop showing the result because it's kind of getting in the way. And let me stop plotting the second one because that's never giving me what I want. Let me go from range of minus 20 to 20. And finally, I'm going to print, I guess that's good enough. Let me go from minus 10 to 10. And I guess the quickest way to do it is this. Because the scale won't be exactly the same. Let me actually do, sorry, one last thing. I want absolute squared of all of this. So that should give me the probability density when it's done drawing. And this probability density is, so the kind of, it's on a different scale, that's why I'm drawing this one by hand. This is the potential energy, kinda, more or less. This is the, close enough. So this is the potential energy, 1/2 m omega naught squared x squared. And the way it kind of matches up around here. Around here, this should be the energy level. This should be this is my E22. Yeah? So this is the question. How does this agree with your classical intuition about a behavior you expect to see in a classical oscillator? Like, what feature do you see here that's noticeable?
Most of it is in the
You're looking at this shape, right? Kind of concave up. And since this is probability density, what that means, most of that, like the highest probability of particle being found is up here or here. So let me translate that into classical version of what the similar statement would be. It would be saying that, all right, so I have this oscillator. This is my x equals 0 position. And imagine I've displaced it and then let it move up and down. And I guess what it's saying is somehow if at some random moment in time I measure position of this mass, it's somehow saying that it's more likely to be found towards the end point than towards the equilibrium position. Is that the case? Classically? That this mass is more likely, at just a random moment in time, it's more, let's try to do it this way. Let's do a quick experiment. All right, let me divide my world into 3 regions. So regions 1, 2, 3. Yeah? I'm just going to say, I'm going to turn around, and I'm just going to, without looking, I'm just going to say at some moment the phrase, I guess, now. And at that moment, just I'm going to say that about, I want to be statistically correct. Let me say that 20 times. One of you keep the number of times it's found in regions 1 or 3. Or sorry, somebody keep a number of times it's in region 1. Who wants to do that? Okay. And who wants to keep a number of times it's in region 2? 가오제? Who? Okay. Zenkai will do region 3. So, all right, so let me start it off, and then I'm going to turn around, and I'll just say it now whenever I feel like saying it. Ready, set, go. Now. 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 I can't be rhythmic. Now. 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 I think I'm waiting the same amount of time, right? So I have to break up the rhythm somehow. It's hard. Now. 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 Next two are going to come quickly. Now. 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 Okay. I guess I have 5 more. I'll do 5 more. Now. 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 Yeah, I got bored. Okay. Kevin, could you give me your count? 10 times. Gaoje, your number.
100. I'm sorry, I messed it up.
All right. So we can figure that. Zenkai, do you have your count? About 5. All right, so it should be 5. So, because I did it 20 times. Yeah. So, all right, so it's with small numbers, you don't quite see it. But a pattern that's beginning to emerge is that this mass is more likely to be found near the ends than in the center. Because like if they were all equal probability, then it should have been, like a 7, 7, 7 or something close to that. Or if it's more likely to be found in the center, then maybe this should have been 10. But it's not the case. It's that it's actually more frequently occurring near the edge. Why do you think that is? Like now that you see kind of that maybe being the result, like can you come up with a reason why that should be the case?
Because the velocity is smaller at the endpoint.
Yeah, you look at the velocity. So it spends more time in this range and here than the amount of time it spends here. So, and that's what this quantum mechanical result is showing too. Even though this says, this doesn't explicitly deal with the velocity, the probability of the particle being found near the classical turning point is greater than the probability of being found where the kinetic energy is largest. So this is an illustration of correspondence principle that way. And your textbook does, spend more time talking about it, so you can read through it. And this dotted line it's showing is actually the classical probability. That's why it goes to suddenly. Anyways, yeah, I guess that's all we have time for with the harmonic oscillator. But before we move on, any questions with the harmonic oscillator? I know we went through it quickly, but so what you are expected to know with the harmonic oscillator is fairly basic. Like the only thing you would have to memorize, if anything, would be this, the energy eigenvalues. Yes?
Do we have a real example of quantum harmonic oscillator? Like for the classical one, we can imagine some picture. For this one, what does this look like?
Yeah, I think I mentioned this before. So the reason we spend so much time with oscillators is that almost any stable equilibrium can be approximated as a harmonic oscillator. Almost any stable equilibrium. Let me show you what I mean. So let me just draw up an arbitrary potential. I mean truly arbitrary. So some kind of smooth potential energy curve that looks, I don't know. Let me just draw one that looks like this. Just an arbitrary potential, something like this, right? And if so this is a potential energy as a function of position, and if a particle were to start out here, then it would just roll down into infinity here. All right, so let's find some stable equilibrium, positions for a stable equilibrium. So there are equilibriums. This is an equilibrium point. This is an equilibrium point. This is equilibrium. This is another equilibrium, right? So this is an unstable equilibrium because if a particle is exactly at this position, it will feel zero force, but it moves a little bit either way, it'll roll away either way. So this is a stable equilibrium, right? So at stable equilibrium, these are some of the features that you can say. One of the features you can say is that first derivative of the potential function is zero, right? Net force has to be zero. And second derivative of the potential function has to be positive. Because if it's negative, then it would be unstable equilibrium. So imagine, so taking this potential. So potential as a function of x, it's some complicated function. But what you are going to do is you are going to expand it around x naught. Imagine doing a Taylor polynomial expansion of the function around the x naught. Then what that would look like is, all right, the constant v naught plus the first derivative at x naught times x minus x naught plus the second derivative at x naught of 1/2 x minus x naught squared plus and so on. Right, that's the Taylor expansion, right? So this is constant. It doesn't really affect anything. This is zero because of this property we talked about, right? Here, for this value here, you get a positive number. You can call that positive number k. So this is the very first non-vanishing term. Using that to approximate this potential, you get your approximate value of potential around x naught is approximately v naught plus 1/2 k x minus x naught squared. Simple harmonic oscillator. So it's a universal. Almost anything that's bound into a stable configuration, you can come up with a form where it's represented like a simple harmonic oscillator. Some of the more common ones would be molecules. So molecules are bound at a distance. If you try to pull them apart, there's a restoring force. If you try to push them close, there's also restoring force. So molecules have a vibrating mode. And the oscillation frequency of that vibrating mode or the energy needed to excite that mode is consistent with what you would predict from quantum mechanical simple harmonic oscillator. And as an example of simple harmonic oscillator, the orbiting object in the rotating frame will behave like a simple harmonic oscillator because there's just the right speed and the radius for circular orbit. You displace it a little bit, then it'll oscillate around the circular orbit. So simple harmonic oscillator is universal. It's like, where can't you find the example? We use this spring as an illustration of it because it's easy. But almost any stable equilibrium can be represented with a simple harmonic oscillator potential as an approximation. All right, welcome back. So this is a quick demonstration of what I was saying about this interference being more general than waves, which is already pretty general. So this is there are mathematical analogs to this in quantum mechanics and other things. So let me just show this to you. It's a coupled oscillator. So the normal demonstration goes like this. I have two pendulums. You know what pendulums are? Like nothing surprising there. I can set one of these two pendulums in motion, and this is what you will see over time. Over time, you will see this motion transfer over to the other pendulum. And when you wait long enough, you will see, are they at least closer? Yeah. All right, if they're closer, let's try it. All right. Let me start out with this one. I trusted this better. Okay, so over time, when they're matched, this comes to a stop, like right now here, and you wait long enough, and the motion will transfer back. So this is a demonstration of something called a coupled oscillator. And you can kind of reason mechanically how this happens. The pendulum has some natural oscillation frequency, and as this shakes, you see the whole stand shaking, right? That happens to match the natural oscillation frequency of the other pendulum. So that sets up a resonance and goes that way. That's one way of looking at it. Let me show you the other way that can be that's similar to interference. You can look at this motion as an interference of two different types of motion. One type of motion is this, where they move together like this. That's one type of motion. You will see that when I set up the motion like this, they move together forever. They don't ever do anything else. So what you saw before this is an interference of this and this motion. This is another stationary state, where when it's set in motion like this, it'll always move like that. So the way you can describe this motion that you saw as interference between this and this. So at time equals 0, these two types of motion, case A and B, are in phase. Case A and B are in phase. That results in this portion being at 0, this portion being looking like this. And when you look at it carefully, these two oscillation modes, they have different frequency. So over time, they go out of phase. As they go out of phase, eventually this will come to stop and this will move more. That's what you are seeing. So I just want you to show this as an example of types of takes a similar kind of mathematical operation as what we are doing right now. And this is not wave, it's an oscillation strictly. But it can be described using the same tools that we are talking about, using the same language, same everything. All right, that's 5 minutes. All right, let's move on to what we are actually doing today. So it's something that we don't quite cover, and I think I entertained for a bit if I might try covering it this semester, and I don't think we will. But what I do want to cover instead is just talking through qualitative features of what you see with the finite square well. And I think if we are just talking about it with help of simulation, I think that's something that we can definitely do without things being much too complicated. So that's what I wanted to do today, maybe for first 10, 15 minutes or so. And I'm hoping to have somewhere between 30 to... So this is a finite square well, and the kind of interesting things that you could see with a finite square well, and some of the features that you can see that kind of resemble the solutions you have seen in infinite square well. The difference basically is, this sinusoidal looking thing, how quickly do they go to 0 at the barrier. So I guess I'm a little bit over the amount of time that I wanted to spend on this. Let me just show you one thing. So the states you are seeing here, they are called stationary states, really for a reason. And I think right now it's difficult for you to really see because it is just so darn stationary that, like, what else can be there? It's because it's right now displaying probability density. Let me have it display wave function. Then we can talk a little bit more about in what sense these energy eigenstates are stationary. Because when I'm displaying wave function, let me make it fast. It actually doesn't look that stationary. It oscillates, it has time dependence. So why are we calling it stationary state? It's easier to see if you show more parts of the wave function. So right now I'm displaying the real part and imaginary part of the wave function. Okay, that also doesn't really show how, in what sense these states are stationary. Okay, let me make it so that it's showing, instead of the, wave function is complex, and any complex number function is two parameters, and you can decide those two parameters in two different ways, or two or more ways. One is to do it this real and imaginary part. That's almost like a Cartesian representation. Or you could do it with a magnitude and phase. That's like a polar representation. Magnitude is how, the magnitude of the wave function at those positions, and phase is the complex phase factor, which would represent the angles in the complex plane. So with this representation, let's see here. And you will see things do change over time. And what is changing over time is the phase, not the magnitude. And if you kind of recall back to the representation of real and imaginary part, you can kind of track it here. If you imagine doing the real part squared plus the imaginary part squared, and then that square root, that part actually is constant. And that's what this magnitude and phase representation shows, that the phase is changing over time according to the time evolution dictated by the Schrodinger equation, the time-dependent one, but the magnitude remains the same. This is something that holds for all stationary states, all energy eigenstates. Now, we can construct something called the superposition state, and that's where fun things can happen. So it says create a superposition state by setting coefficients such that, okay, let me look at here. So this is my first state. My second state is, oh wait, where's my E2? Oh, E2. Oh, I see. I think I know what it's showing. So let me deal with one of the higher energy states, because at E1 and E2, these are such a, well, maybe I can do that. Let me do that. So you see these kind of doublets of energy levels. It's because with these two wells that are pretty close to each other, you have like an even state, that's E1, and odd state, E2, or sorry, by even, I mean even symmetry with respect to the center of the whole potential wave. It's even on reflection, and this is odd on reflection. And I think it's the even states that have lower energy than the odd states here. So, and both of the even states, either by themselves, so, this is all stationary state, even state, or the odd state, they are stationary states. And with the other states, with this representation, what you're seeing is the phase on this part is pi, or 180 degrees different from this side, which is why you are seeing the color jump so suddenly. Okay, that's as interesting as stationary states are gonna get. Now, what I can do is I can form a superposition of this odd. Okay, let me go back to this. Of this odd state and this even state. And by superposition, I simply mean adding these two components together. And when I have both psi1 and psi2 displayed, you can kind of guess what you will get when you add these two states together. So let me form the superposition state here. For psi2, I have 1. And let me put in 1 for psi1 as well. So when I do that, normalize and apply. Okay. So this is the normalized superposition state of those two energy eigenstates. And you kind of see a wave function that you could describe as being kind of a, in this double well setup, if you put in a particle into one of the two wells, this is kind of the wave function that could represent it. And watch what happens as I let the time run. Over time, this wave function, do I want this to go a little faster? Over time, this wave function moves to the right side of the well, and over time, it actually moves to the left side of the well. And this is a kind of a superposition bit phenomenon. There's actually a really close analogy between what you see here. And I think you saw a demonstration of this when we were doing interference way back with optics. I had a physical demo of coupled oscillators, coupled pendulum. When you set up an oscillation in one pendulum, over time that oscillation moves to the other pendulum. And I wanted to show that demo because that's a kind of physical classical oscillation demo that relates to this kind of quantum mechanical phenomena. And yeah, and I guess I'll leave that here. You can play with it, and you can kind of see if you show real and imaginary parts. Can you show that better? Oh, maybe not. Not any more clearly. It's kind of a bit phenomenon. So the reason the superposition of these two energy eigenstates won't be a stationary state over time, if you plot probability density, it does actually change over time. It you can make draw a direct connection between the frequency at which this probability density oscillates between these two and the bit frequency between these two energy eigenstates. The frequency at which this oscillates back and forth, you can relate that to the energy difference here of 0.02, associated frequency through Planck's constant, and you'll get something like that. So, all right, I think I spent more time on this simulation than I really had. So I'll end it here, and again, this is kind of downside of the limited amount of time we have in this class, which is we don't have enough time to explore these more thoroughly. So, if you want to, some level of guidance that is given here is, let me just clear all the drawings, is, in this simulation. And, part C is where I don't quite have detailed descriptions, but what I am referring to here is it's able to demonstrate the difference between states referred to as a stationary state, energy eigenstate, and the superposition state of different energy eigenstates, which can show time dependence on probability density and all that stuff.